a definite integral this time, and we're going to use the substitution x equals tan theta, and that gives us dx on d theta be equal to sec squared, so that I can change variable in a minute, but I also need to account for these boundaries. So when x equals 1 on root 3, the angle that corresponds to that is pi on 6, and when x equals 1, the angle that corresponds to that, for tan anyway, is pi on 4. Okay, now I've got all my pieces, I'm going to substitute in. Here we go. My new boundaries are from pi on 6 to pi on 4. Then what you've got here, this dx is going to become a sec squared theta d theta. So I'll stick that on the numerator there. Okay, what am I going to get on the bottom? Well, that x squared is going to turn into tan squared, and then you've got the square root of 1 plus tan squared there. Okay, now this here is an identity that we need to recognize. 1 plus tan squared is sec squared, so when I do the square root, that's just going to give me, do the boundaries first, that's just going to give me sec. So I've got tan squared here and one lot of sec there, all with respect to theta. Okay, so you can see that one of the secs will cancel. There you go. Okay, and so now I've got, well, what's useful here? This is a 1 over cos on the top. So that means a cos is going to cancel down here. So I've got these boundaries that are the same. Okay, what are you going to get? This is actually sine squared on cos squared, but one of the coses will cancel. So I'm going to get sine squared on just one cos, not cos squared. Okay, there we go. Almost there. Have all these boundaries in place here. I'm dividing by dividing cos, so that's the same as multiplying by cos. And now we're in a position where you can see this is reverse chain rule. You've got cos theta and sine theta to the power of -2, but the useful thing is that cos theta is just the derivative of sine theta. And if you're not so sure about that, you can say, you know, let u equal sine theta, so du on d theta equals cos theta. You could do the substitution again, but it's a bit long in the tooth, being we've already done one substitution up here. So I'm just going to go straight into the fact that this is -1 on sine theta to the power of -1, because this is -2. The powers come up once. So there are our boundaries as before, and now I can evaluate this thing. This is going to be -1 on sine pi on 4, minus -1 on sine pi on 6. This guy is 1 on root 2, so his reciprocal will just be root 2. I got a double negative happening there. This guy is a half, so his reciprocal is just 2, and then we'll just put him round the right way so that everything's nice and neat. And that's it. Another definite integral that we can do with a trig substitution, and this is the one that gets provided to us. So we'll do the derivative so we can change variable in the integral in a second. So that's going to be the derivative of the inside there will be sec squared, and then the power will reduce by 1. You also have to change your boundaries. So you've got x equals 0 over here as your lower boundary. That gives you theta equals 0 as well. And you got x equals 1, which in this case is theta equals pi on 4 once you stick 1 in there and solve. Okay, so now we've got all our pieces, we can do our substitution. We're not from 0 to 1 anymore, we're from 0 to pi on 4. Then I've got a square root of x. Now I'm just going to consider that as tan theta, because the square root has to be positive. And then you've got 1 plus tan squared, which is the actual just standard substitution there. Now instead of a dx, I'll write 2 sec squared tan d theta. Okay, so I'm going to get this 2 sec squared tan d theta. Okay, just enough room. Great. Now you can see that on the denominator here, 1 plus tan squared, that's an identity. That's just sec squared. So in fact, I'm going to cancel that with that. Okay, so now that leaves you with 0 to pi on 4. I'll stick that 2 at the front because it's a constant I don't need to worry about. Tan times tan, that's tan squared. Okay, now tan squared we don't have a nice simple integral for, but we can use an identity to show that it's equal to something that is, namely sec squared minus 1. That's easy to do, and you can get that identity from the Pythagorean relationship there. So sec squared integrates into tan, and -1 integrates into theta from 0 to pi on 4. Okay, so now I've got that 2 out the front. This is going to be tan pi on 4 minus pi on 4, and when you evaluate both of these at 0, you just get 0. So I've got tan pi on 4, which is just 1, and that's just a pi on 4, so you get 2 minus pi on 2. Okay, last one for today. I've got an integral which I can do by substitution, and this is the one that they give us, x equals 4 sine squared theta. So to change variable, I've got my dx on d theta over here. That is going to be, this is sine theta to the power of 2, so I'm going to bring that 2 out the front. I'm going to reduce the power by 1, and then I'm going to multiply by the derivative of the inside function, which was just sine, and its derivative is cos. I also need to change my boundaries. So x equals 0 over here. The angle that corresponds to that for this will be 0. Now when x equals 2, I better do the working just to make sure I get this right. You get 2 equals 4 sine squared theta. So that means you got sine squared theta equals a half. And just taking the positive case for this one, I get sine theta equals 1 on root 2. So the angle that corresponds to that is pi on 4. Right, so now I can do all of my substitutions. I'm now from 0 to pi on 4, and what I've got underneath the square root is, that's the x term just there, which is 4 sine squared theta, like they told us to put in. Then you've got 4 minus 4 sine squared theta, and instead of dx, I'm going to have kind of this monstrous thing in here. I'm going to run out of space, I can tell. It's going to be multiplied by 8 sine theta, I'll just put it continuing down here, cos theta d theta. Okay, so there's some cancelling that's going to happen here. For starters, this is sine squared up here, and I've got a cos squared down here. Okay, but they're going to be both by a factor of 4, which I can cancel, and they're both going to be taken the square root of, so the squares will vanish. So that's why I'm going to go straight from this to, that's going to be sine over cos. That's it. That's all this whole square root thing evaluates to. I could write that as tan, but there's not much point, because what I want to do is cancel immediately these cos terms I can see here. Cancel, cancel. Okay, good. So what I'll do is I'll take, I've got a sine squared here. I've got 8 of them. I'm going to take a factor of 4 out, because I still want 2 in the brackets, like this, because that'll allow me to use my double angle for cos in here, and it's simply, from 0 to pi on 4, it's 1 minus cos 2 theta, which you can verify by expanding that, and then you can see the relationship between these two, okay, with respect to theta. Okay, so now I'm in a place where I can integrate, so I've got a 4 out there, 1 turns into a theta, this is just going to be a half sine 2 theta, from 0 to pi on 4. I don't like that half hanging around there, so I'm just going to stick a 2 inside the brackets, which will give me this, from 0 to pi on 4. And now I'll evaluate this guy. I'm going to get, there's the 2 outside the front, 2 times pi on 4 is pi on 2, and I've got sine pi on 2 as well. When you evaluate both of these at 0, you get 0. Okay, sine pi on 2 is just 1, so this is going to be 2 times pi on 2, which is pi, minus 2 times 1, which is 2. And that's it.